Good afternoon, everyone. Welcome to the third lecture of or the third online session of our course about machine learning. And we have already studied in the previous two lectures just like overview of the machine learning concepts of machine learning. And in part two, which is started today, and it will continue for three lectures, it will be mainly for the supervised learning. Supervised learning, either in like regression or in clustering. So this is the topic of the of part two. So part two, we start with the most like basic form of learning, which is known as regression. We start with the linear regression, is the one of the simplest algorithms in order to learn from data, to build some mapping that it can predict the outcomes for inputs that were not part of the training. So we will talk about these basic concepts for into today online session. However, as I always remind you that I'm not going to repeat the whole lecture again because the lecture is already recorded, so you can watch it online, but I will focus on the major message from this topic. So now I will share the presentation, but as I said, that I'm not going to present it as slide by slide. Just I will focus on a few parts of this lecture. Yes. Yep. So now you can see in front of you the part two, and part two is mainly about regression and supervised learning, and we will talk also a little about clustering. So the idea here that we will start with the linear regression, and this will be mainly the topic of today. So we will talk about simple two dimensions, and where we can introduce the main concept. Then we will generalize to n dimensions and with computer implementation. We will talk also about nonlinear regression. So in next lecture, we will talk more about this nonlinear regression using linear equations, and we will start the topic of neural networks, and we will see how these neural networks could be learned by using some like optimization techniques like stochastic gradient algorithm and the steepest descent. And also we will introduce the multi-layer neural networks, and we will give some concepts of deep learning and pattern recognition. In the third lecture, we will talk more about classification algorithms and rules of learning, like based on data, and also a general overview of supervised machine learning. So this will be the outlines of part two. So what is the regression? So regression actually is the idea of regression basically is how to optimize or to construct mathematical equation which represents the data. So you have data, okay, and this data, it has input and output. The output of this data, we call it like the labels if we talk about classification, or it can be regression, it can be numbers representing the output of the data. I will give like numerous examples for you to understand what that means. But we have data as input, and then we have output of this data. So we know the input and the output, and this is called the history. So we have history, we have database contains such kind of data. This data can be huge, can be several like hundreds of gigabytes or thousands of gigabytes, can be small. So it depends. And then instead of dealing or keeping this data, we want, or our mission, our aim is to build some mathematical equation that it can represent all this data with generalization like properties. Generalization means that it like, between quotation, it like understanding the relation between the input and the output. It is not memorization. I am not interested to memorize this data. I can memorize this data in my flash memory, but memorization is not generalization. So I am not interested in memorize the data and it is at their output, but I am more interested in understanding the connection or the mapping between the output and the input. What is the most proper function that it can do that? So we have two primary approaches. We have parametric regression and we have black box regression. In the parametric regression is something like you having linear function or nonlinear function, but this function is finite, is clear for us, okay? And there are some parameters in this function, and we like to tune those parameters in order to make this function as close as possible to represent the data that we have. And then we have the black box regression. Be careful that black box regression doesn't mean that it is non-parametric. It is still parametric also. But the black box, that you don't know what is the relation between the parameters inside this equation and the outcomes on the input and the output. So the relation is black box for us. So we don't know. We know that there are some internal, maybe hundreds of millions of parameters, like in ChatGPT. They are adapted all the time in order to get the relation between the input and the output. But we don't know what is the impact of each parameter or what is the function of each parameter in that black box. So it is for us a black box, but it doesn't mean that it is not parametric. It is parametric. We have already parameters inside that we need to update. Okay?
Ei paran, mä oon täällä tunnilla. Mikä sun asia?
Could you please just
Joo.
mute that? Okay.
Kotona olen tunnilla. Minulla ei ole aika, rakas.
So just
Se 3
okay. I just muted. Okay. Yeah. So what is the simplest linear regression algorithm? The simplest one is that the one that it has only two parameters. Okay. So if you have two parameters, let's say have the case where okay, because I'm thinking to have different examples in for you who came from different backgrounds to understand what I mean. Okay, so now if I'm thinking that X is the age of person and Y is the probability that this guy has diabetes. Okay, so we have data, previous data with ages and the health status of the person. So it is two parameters case. Okay. We can have different example. For example, the vibration of a motor. So we have motor or engine. We have sensor. This sensor is measuring the vibration. So X is the vibration. Y is the time before first fault has happened. Okay, so we have vibration of motor. Okay, and then we have this parameter increasing the vibration. okay? The frequency, for example, of the vibration. And based on history, we have data set that when the vibration was that much, this machine got fault after 1 month. That one after like 60 days. That one after 35 days and 20 hours and blah, blah, blah. So this vibration and fault, okay? We can have, for example, another example from startups. X can be the capital money of the startup, and Y can be the value of this company after 5 years. Okay, so we guess that there might be a relation between X and Y. You can think about many examples that include this very simple case, only two-dimensional problem. Okay, of course, with two-dimensional problem, usually we have very limited accuracy because we put this is X is called the attribute and Y is the outcome. So usually we have in real problems we have many attributes, not single attribute. But we just start with this simple case of the simplest linear regression, simplest possible linear regression. Okay, now our aim is to find the best line which can represent the data that we have. So this is the way that we can represent the data, that the outcomes y will be alpha x plus beta. What are the parameters that we want to tune based on data is alpha and beta. Alpha representing the slope of the line. Okay, you can see that when alpha equal to 5, we have this slope. When alpha equal to 2, we have lower slope. If alpha equal to 0, we have just line like this and so on. This is alpha equal to -2 and so on. So alpha represents the slope of the line and beta is the offset of the line or shift. Okay, so this is beta equal to 1, beta equal to -1. It can go down and up and so on. So beta represent the offset or the shift, and alpha representing the slope of that line. Our mission is to find what is the optimum or what are the best values of alpha and beta, which makes this equation is fitting very well with the available data. Okay, so to do that, we need to define, we have to put criteria. Keep it like for, and everyone should know that when you say best, or you say this is the best possible outcome, or the optimum, or the minimum, when you talk with this language, you have to have some criteria based on what? It is the best based on what? So this is very simple, this is very, very obvious actually. For example, when I am like revising one paper, like publishing paper, that under review, when I am a reviewer for that paper, when I find the author talking about that his or her algorithm is the optimum or is the best, and then I check optimum based on what criteria or best based on what. If this was not defined, of course I immediately reject the paper, or sometimes I just send that hard review that it needs to be fixing this like serious gap in the research. Always when you talk about best, optimum, then the first question comes: optimum on what sense? Best on what criteria? When we say that alpha and beta needs to be the optimum ones, okay, then the question: optimum based on what? Okay, or best based on what criteria? To define the criteria, what I did here, we define the error, because it is intuitive to say that optimum means that the algorithm will have the minimum error based on the data available. Okay, now we have data, as you can see, we have X and Y. So we have X1, X2 up to Xn, and then we have Y1, Y2 up to Yn. Our question is to find alpha and beta. What I did here, so if we take Xi, the ith input, this is the attribute. The input is the attribute or the feature. Okay, as I said, the age of person, age of car, vibration, stock market price, and so on. So now this is Xi, the attribute. And then we have this line. You can see the line is in red. This line representing the curve that I want to find the best one. And this line is controlled by alpha and beta. Okay, so if you look to Xi, then the point on the line will be Yi. And this Yi hat, I put it Yi hat because I have real Yi from the data, from the table that I have, and then I have Yi hat is the value over that curve. My now aim is to find what is the minimum error. The error is defined as the difference between Yi, the real Yi, and the expected Yi over the line. Then you can see here I can define, this is for example E1, this is E2, error 2, E3, error 3, error 4, error 5, error 6, and error 7. And it is obviously that for you that these errors can be positive and can be negative. So it is clearly, we cannot just sum the errors because I am looking to minimize the total error, not the error at only one point. For example, if I have in this table a 20 point, I am looking to have the line which minimize the average error over all these 20 lines or 20 points, sorry. So when you have, if you take just the summation of the errors, okay, some of the errors are positive, some of the errors are negative, they will cancel each other. And then this will give like wrong result because it will not represent the real errors in this case. So in order to find the best representation of the total error, we can either take the absolute value of the errors, okay, because I am interested to the error itself, not in its direction. It doesn't matter if the error is positive or negative. It is error at the end. So we need to minimize that total error or the average error. One way is to minimize over the total absolute value of the errors, or we can minimize over the error square. Okay, we can minimize over the error square. So this is the average square error. This is the average square error. I divide over the number of points, and I take the summation over the whole error square. I take square again to get rid from the sign of the error because it doesn't matter, positive or negative. And the second thing that when we take the error square, this also it has some physical meaning here, as I will explain. But anyhow, these errors is called the norm of the error vector. If we take the absolute value, it is called norm 1. If we take the square, it is called, as it is shown here, norm 2. If you take the absolute value, but you take the cube, but you need to take the absolute value first because a cube can keep the sign, then it is called norm 3 and norm 4 up to norm infinity. The norm infinity is only taking the highest error. So you are looking only to the highest error and you try to minimize the highest error or the largest error. Okay, I will not go deep in this. It is well known from linear algebra and from estimation theory, but we talk about it later in the future when we talk about probability and stochastic algorithms or the learning algorithms based on like Bayesian and the probability theory. But anyhow, now we take the average of the square errors, then I can minimize this error. Okay. I said that taking the square of the error, it can have also physical meaning. Yes. Because if we are talking about in signals, for example, for those who came from electrical engineering, if this outcome is voltage, okay, when we take the voltage square, or if it is current also, if we take the current square, usually we talk about power in this case. So minimizing the power, it has meaning, because the power is what is matter in many applications. So the power of the error is what we are looking to minimize. Sometimes, even if you have the voltage high, but the current is zero, so the power is zero. So this is one physical like interpretation, at least for norm 2. And we can see later that norm 2 is the optimum norm in case of if you have Gaussian noise. But now forget this. Let us talk about this problem in simplest possible way. So now this will be 1 over n summation from I equal to 1 up to n. This is the actual y in the table minus y of the function. And then I remove this one and I put the function itself. So the function is alpha xi minus beta. And because we have sign minus here, so the minus will be also distributed here. So it will be minus alpha xi minus beta. It is clear that this equation is a quadratic equation and it is convex. I hope that you revised the previous lecture when we talk about this. I gave some examples also, solved examples by video in model. So I hope that you watched that. So you, if you watched those, you will understand what I'm doing now. So now I want to minimize this error, this psi. I want to minimize the error. Minimizing the error based on what? Alpha and beta. So what are the optimum alpha and beta that minimize the error? So we can do that by taking the differentiation of alpha of xi with respect to alpha and with xi with respect to beta. So it will be simply like that. So this was explained in details in the previous lecture, okay, and it is recorded. And also I put some videos on how to do that by hand. So I hope that you watched that one. Okay. There is a question now on the chat that isn't the actual y, the line going across the graph representing, yes, yes, it is y is the actual y is the actual, and y hat is representing by alpha x plus beta. Okay, so that when you take the sorry, let me go back. So when you take this minus, then the result will be the error. This is the error. This is not error. Yi is the output. Yi hat is the output of the function. But when you subtract them, then you have the error. Okay, is it clear? Okay. Okay. So you got it. Good. Good. Yep. Then I take the differentiation of xi with respect to alpha and with respect to beta and put them equal to 0. In order to find alpha and beta. By solving this, it is a second order equation, so it is very easy, very straightforward to solve. You just square, you take the 2 outside, and then differentiate what is inside. So then you will get this equation. This is the first equation, and this is the second equation. So you can see that both equations are linear equations in two unknowns. So we have linear equations because this is the summation of xi square. You can count it from the table. Summation of xi, you can count it from the table. Summation of xi times yi, you can find it from the table. okay, the given table. And the same here for this second equation. And what we have here, the unknowns are alpha and beta. Then I have two equations into two unknowns. This can be easily solved, okay, in this way. We have this matrix, 2 by 2 matrix, and we have two unknowns, and this equal to this result. Remember that every summation here can be computed from the table itself. Then I can find the optimum alpha and beta to have this one. So this is the mathematical foundation for solving this. But let us take this example in order to clarify things how it works. Here they say that to automate price estimation for second-hand Volvo cars. So we assume that you want to build a website by yourself that it can estimate the price of second-hand Volvo cars. I specified the car brand because I don't want to put many attributes, but this will be extended later, okay? So now you have table like this one. You have the age of the car. Assume that specifically one type car, maybe XC70 or XC90 car, Volvo car. This is the brand of the car. And then you have history. You went to some website which sell used cars. You collected information from there about Volvo, the same brand, and you check the years of the car. So this one means that it has been manufactured or at least started. It is first working before 25 years. This car, which its age is 25 years, was sold at 730 euro. This one at 30 years, but it was sold at 3,900 euros. So maybe you feel a little bit confused why this is older, but it sold at higher price. Actually, the reason, because we don't have other attributes. Maybe this car has, even it is older, but it has better shape. But this one, maybe it has like crashed or something. So we don't know. But this was the prices of the cars and the age of each car. Okay. So the table, this is the table that you have. So you have X1, Y1, X2, Y2, X3, Y3, and so on. Okay. Now I want to find what is the optimum alpha and beta. This one, what is the optimum alpha and beta that represent the prices of these cars? I can build the matrix in this form. So I need to take summation of xi square, summation of xi, summation of xi, and n. N is the number of data. It is clear that the number of data here that we have 7, 1, 2, 3, 4, 5, 6, 7. N is equal to 7. Okay, so this is 7 here, you can see. And summation of xi, you just take the summation 25 plus 30 plus 15 plus 8 plus 17 plus 10 plus 12. And this gives you 117. Then you take summation of xi square, 25 square plus 30 square plus 15 square, and so on. So you get 2,347. Then you need to summation of yi, 730 plus 3,900 plus, and the result is 40,073. And finally, you take the cross summation is xi times yi. So 25 times 730 plus 30 times 3,900 plus 15 times 3,800, and so on. So you got this result. Now I can put these results in the same shape like this one. So I have now two equations into two unknowns. What is the optimum alpha and beta? By solving these two equations into two unknowns, where I expect that, of course, it is something from primary school that everyone can do that. But Even you don't need to do it by hand because you can do it by computer or by calculator. So after solving this alpha and beta, we got alpha equal to minus 381 and beta equal to 12,186. So this is the equation. Now we have this equation y equal to minus 381 times x plus 12,186. So far, you cannot say if this equation is accurate or not. Okay? You cannot say that. But still, this equation can tell you something. It tells you that if the car is new, you can put x equal to 0. So if you put x equal to 0, then y equal to 12,186 euro. For me, it is clearly that this number is not accurate at all. In new Volvo cars, it can be minimum 25,000 for the cheapest one. It can be 40,000, 50,000, 60,000. So this equation actually, it seems that for a new car, it will not give me any good answer. But this is not enough actually. I need to check the performance of this equation. Is it good or not? To do that, we need some extra points. We need to check some validation. So I went again to the website and I drawn from there some extra data, and I want to check this data with my equation, with my mapping. Before I continue, I check the chat if you have questions. Does the accuracy of the optimal parameters decrease with, you mean the accuracy should increase with larger amount of data? Generally, yes. In general, but not necessary. Why? Because, for example, in this example, I gave only one attribute. So with this, a single attribute, which is the age of the car, maybe if you get larger data, you can for sure improve a little bit the accuracy, but at some point you cannot increase it anymore because you have actually missing important information: the status of the car, the gearbox of the car, is it manual or automatic? Is it electrical car or diesel car or benzene car? What is the color of the car? What is the brand of the car? So we have too many other attributes to increase the accuracy. But generally, yes, increasing the data, if you have like accurate data, of course, this should at least slightly increase the accuracy of this equation. Now you can see this is the optimum curve, as you can see, and it looks logical. As the car age increases, the prices will decrease. So generally the trend is okay, but is it accurate? The total error here, if you look to the total error with the data, so it gives you this is the variance. Okay, the error square is equal to 5.3 times 10 to the power 6. Now I went to the website, as I said, and I drawn from there, or I took from there 3 new data, which was not bought from the training. So this new data, I have this age, 5 years, it was sold at 7,000 euro. With 9 years, it was sold at 2,600. With 22 years, it was sold at 9,900 euro. I applied these numbers in my equation, my deduced equation, this one. So I put here x equal to 5 as a new data, and I want to check what is the expected sold price based on my trained algorithm. So it gives me here, it should paid or should sold at 10,000 euro, but it was 7,000. So there is big error here. At 9 years, my algorithm told me that this car should have been sold at 8,757, but actually it was sold at 2,600 euro, much less. At 22 years, my algorithm told me that this car should have been sold at 3,800, but actually it was sold at 9,900. So I can see now that the model was bad. The trained model was bad. And now I need to think about the reason why this model was bad. Before that, I check the chat. What you have other questions? Yes. Yes, this is good discussion going on the chat. So I can continue this. Yes, I agree. So now if we continue to think about what are the possible reasons that your algorithm was not, or my algorithm was not doing that well. Sorry. There are several reasons actually. The first reason, and keep in mind that those reasons will be valid for any regression or any learning, any supervised learning algorithm. These reasons are valid. Okay. The first thing is insufficient input features. And this is very, very important actually. So you cannot decide the price of the car based only on its age. It is not enough. Can you yourself, can you buy a car by knowing only its age? Except of course it is new. This is something else. But can you blindly buy a car based on age only? If I told you I have Mercedes car, it is manufactured at 2025 and it costs 1,000 euro. Can you pay immediately for that? Of course you shouldn't, because that car may be in very bad, like maybe burned, maybe it has very bad crash, that it is useless. There is no way to sell the car only as rubbish, only to melt the iron. Just that's it. So the car maybe doesn't worth more than 200 euro. So you cannot pay based only on the age of the car. You need to ask some questions. So it is the same here with this algorithm. So insufficient input features, sometimes we call it features, sometimes we call them attributes. So we use both terminologies. So the input features like the mileage of the car, engine type, overall condition, color, additional comfort, safety features, many other features that we have to know in order to build precise and accurate model. The second thing, incorrect model assumption. Yes, it can be sometimes that because we assume that the model is linear, but it might not. It might be if we deal with the quadratic equation, it will be better. It can be, of course, I'm not talking about the prices of the car, but in general, sometimes I need to take the cosine or the exponent of minus of some alpha times x. It will give me much better representation of data. So incorrect model assumption is one possible reason for this error. Limited data set size, as you mentioned in the chat. So the data set, maybe it is too small to capture the relationship between the input and the desired output. So it becomes very hard to generalize the result. Data quality issues. This can be one reason. Data quality, for example, if your data is noisy, If the website, you know that some people, they buys the price. For example, I have a car, and then I sold my car, and I want to say that I sold my car at good price. I don't want to say that I sold my car at only 2,000 euro. So when you ask me, I told you that, okay, I sold it at 4,000 euro. Actually, I sold it at 2,000. So this is biasing now. The data is biased data. So if you take this, my word, as a truth, and you apply it in your algorithm, then you have biasing in your algorithm. So here the data quality is bad because we have biased data. Some data is rubbish actually. For example, I want to have to put a website. I built myself a website that I am selling cars. I am saying that you can bought your car here to sell it in my website, and I want to show that I sold thousands of cars before. Then I bought many cars and I bought just random selected prices. This is 5,000, this is 8,000, this is 10,000, this is 3,000, and it was just random numbers that I bought. So it will be junk data in this case. So if someone else come to my website and take the data as a real data and they apply them to their algorithm, so garbage in is garbage out. Garbage in is garbage out. So even you apply the best possible deep learning algorithm available, but you put the data, the learning data is garbage. So the resultant algorithm will be garbage as well. It will be useless because it has been trained over biased or random or just meaningless data. Okay. And you can think about other possible causes as well yourself. Okay. So now what I did, it's for me, this input has convinced me that I am looking to have more features. So I went to that website and I picked up two more features. So I picked up the mileage of the car, how many kilometers this car driven, and also the general status of the car, the overall condition of the car. However, the overall condition, and this is very important point, and this is the reason I bought this example in details. After that, I will skip the other parts of these slides because, as I said, it was already recorded. But I want also to focus about important things here. So the overall condition of the car, it is not numeric. Many times it can be subjective. For you, this car is good. For me, this looks bad, or this looks not that good. Maybe not. Maybe we don't have that much difference between human judge in some, at least for the cars. So the overall condition of the car, that it looks, as I said, somehow subjective. It is not a number, but you need to convert it to the number because now we have a numeric regression. So you need to represent this by number. There are several ways. Some of them use fuzzy, for example, fuzzification and so on. But I will make it here simple. So I just, for example, for each car, we assume that I collected the opinion of different people, and then I take the average or I take the majority. So one is the car is very good shape, even it is used, but it is in very good shape. Two, the car is acceptable. And three is the car is in bad condition. Of course, now we have some classes, three different classes. And remember that the problem it will be how to classify the cars that are on the border. For example, if the car, it can be good shape, it can be very good, it can be acceptable. Some people can see this car as a very good, some people they can see it as acceptable. So usually those cars which are at the borderline are those which can make errors. Otherwise, that car is very bad. It is, everyone can say that it is bad condition car. But anyhow, I put some numbers for the overall condition of the car. Also, the mileage, it is not that good to put like very large numbers in my equation. So I was thinking in different way. So instead of saying the actual kilometers of the car, I start to think how people think about the car. Usually people think about a new car. The car is new, or it is fine if it was driven less than 50,000 kilometers. So when you go to the second-hand car, then they can say, hey, this car almost new. It is just driven 40,000 kilometers or only 30,000 kilometers. Does that matter for you if it is 40 or 30? Most people know. Most people know. It is 45,000 or 50,000 or 30,000. Most people, it doesn't matter. So I assume that all these in under one category, and I put it as rank number 1. And I put rank number 2 from 50,000 to 100,000, rank number 3 from 100,000 to 200,000, and number 4 from 200,000 to 350,000. And the engine becomes almost useless if it is driven more than 350,000. If the car, especially if the car is like benzene or petrol car. Some people say that for electrical car, 350,000 is still okay. Also for diesel car, it can manage. But this information now in the attributes are missing as well. But now I have the same table as before, but now with more information. So actually this, for example, explains something. Sorry. Here you can see that because the mileage is under 4 and the status under 2, this explains why the car was sold at quite cheap price. However, this car, even it is 30 years old, but because it driven less, and also the overall condition of the car is very good shape, very nice. The owner of that car was taking care a lot about his car. So now it makes much larger final price than the first one. This now explains something. Okay. Now I don't have only 2 parameters, but I have 4 parameters now. I have the age, I have the mileage, and I have the status of the car. So I need, and of course the drift. Oh, this is the offset of the equation. So I have 4 parameters now I need to find the optimum. So I will follow the same way as I did before. So it is the price of the actual price minus the sold price or the equation price. It will be like that. And now I need to find the differentiation of the total or the mean square error with each parameter, with beta, with alpha, with lambda, with mu. And I put them equal to 0. And then I need to solve now 4 equations into 4 unknowns. So it becomes a little bit more like bigger. I shouldn't say more complicated because it is the same system of linear equations, but with bigger parameters. Of course, as you increase the parameters, the challenges increases. For example, finding the inverse of the equation. And then I have now this equation, and then the optimum alpha, lambda, mu, and beta is equal to the inverse of this matrix times this vector. Then I will get the optimum. And by solving this for the optimum, you will find that this will be the final result. So you can see alpha, lambda, mu, and beta. Okay, and you can see that the average square error is much less than the previous case. And when I tried with the extra validation data, I get even better and more accurate result than before. So this indicates that increasing the features can improve the accuracy considerably, can increase the accuracy. Okay, let me check the chat if you have questions. Of course, if you repeat the data itself, it will not improve the accuracy. If you have the same data, for example, this is important point to say it. What happened if you add from this data, if you multiply this by 2, so 25 times 2 is 58, 4, and you multiply this by 2. So what we got here, actually, we will get some kind of like linear repetition of the same data. So this will increase the redundancy in your data, and this makes also complicated to solve the problem, as we will see later, because you will not the matrix can be, it is called ill-conditioned matrix, and it will generate large errors, and sometimes even it will not have inverse. Okay, so after this we saw the 2 parameters case, 4 parameters case, but in reality we can have generally like M attributes. M attributes, for example, if we have the patient, and in this patient, he has or she has like the age, the height, smoking or not smoking, what kind of diseases they have, the weight, BMI, body mass index, married or not married, have children, doesn't have children. So you can have too many attributes, can be 10, 20 attributes, can be hundreds of attributes in some cases. For example, in image, if we consider each pixel as a feature in the data, and you have 1 million by 1 million, so you can see you have how many attributes that you will have. Of course, we have sometimes in deep learning, when we use convolutional like networks, we can deal with blocks instead of point by point, as we will see later. But in general, we can have a very much larger number of attributes. So it is not nice to use alpha, beta, gamma, and to solve it in the way that we show. So we need to deal with those things as a block in matrix formulation. And we can do that actually, instead of defining alpha, beta, gamma, I use X. So making X is easier. So we have from X1 up to XM, so that we have M attributes. And then we have the parameters that I am looking to find, to optimize, is A. So we have AKI. What is K? K is the number of the data. For example, patient 1 has those attributes, and patient 2 has those attributes, and so on. So this A representing the attributes of each case. So for example, for Y1, patient 1, or engine 1, or motor 1, okay, or certain market. So those are the parameters of the market, so that we have the attributes of the market. And then we have, in this case, in our history data, we have the output and we have the inputs. As you can see, Y1, then I have A11, A12 up to A1M. We have Y2, we have A21, A22 up to A2M. M is the number of attributes, and those the actual outcomes, and those the input. I have this as Excel file or as data that I have. Then I want to build what are the optimum A's that they can represent this equation. Now we go to the general linear regression model, as you can see. So we have the outcomes Y, and we have the matrix A, that it is unknown for me. This is what I am trying to tune to find what is the optimum A. And then we have the attributes that I have from X1 up to XM, and then I have this ones of the offset. Okay, then you can see here that we have y equal to a times x. So I put it in this form. Okay, now what is the error? The error is 1 over n. I will do this exactly the same as we did before. So yi minus yi hat. But nowadays, or now, yi hat is equal to a times x. So this will be in this form. Okay, so you can see that this is the error I made by. This was explained in details in the recorded lecture, so please go back to the recorded lecture, and then you can find the optimum x by solving this equation. Okay, so this will be the optimum x of each attribute. What is the weight of each attribute in order to give us the minimum error, and then this will be the result. So x equal to r inverse times a transpose times y. What is r? R is given here is a transpose times a. You take this a, the values of given in the Excel file, times a transpose. Oh, sorry, a transpose times a. Yes. Sorry, I need just to mute one student. So, okay, so now let us go to our previous example, this one. Okay, so now I have those are A, this is A11, A12, A2, A12, A13, and this is Y1. This will be A, this 30 is A21, A22, A23, and this is Y2. This will be A31, A32, A32, A33, and this will be Y3, and so on. So I will come here to do it in this way. So this is A matrix. From A matrix, if you take transpose multiplied by A, you will get this 4 by 4 matrix. Then the best x is the inverse of this r times the vector of y1, y2, and y3, and so on. So by solving this, you can see you got the same result as we received before. But now it is much easier. So this A matrix and the multiplication of A matrix, most of the programming packages, they can do it internally, like MATLAB or Octave or Julia or Python, all these codes that you can just define what is A. You can take this A from the Excel file and then define what is the output that you want to have. Take this A, multiply A transpose by A by the code, as I will show you, multiply it by the desired output, you will get the result. That's it. Yeah. So that's all about the linear calculations, how to do it. Let me check the chat. Yes, the question here, why do we need to transpose the matrix of A? Actually, this what you can, I mentioned this. Okay. So when you, because when you take the differentiation here, you start by this point. Okay. You start by this point. So here we have yi minus yi hat square. To have this equation, assume that you have vector. And in this vector, you have y1, y2, up to yn. Okay? This vector, this column vector. How can you get this summation? Maybe let me, I hope that I can share with you my my screen. Let me check. Just a minute. I have another screen that I can write with a pen, so I will try to share it with you. What? Yes. Oh. Let me try to share with you the other screen. I don't know if it will work or not. That's it. Desktop. It has not been connected to this, unfortunately. No, it is not possible for some reason that I couldn't share with you the readable screen. But anyhow, by the way, this your question about why it is transposed, it is already in the recorded lecture, but simply that I can maybe try to write something here on the screen using mouse. Yes. So assume that you have this y like this one. Assume that you have here y1 and only y2. Okay. This is the column vector that you have. Now, what happens if you have y transpose times y? Y transpose times y, it will be like this one. It will be y1, y2 multiplied by the same y. So it will be y1, y2. When you multiply the transpose by its value y, what you will get? You will get simply y1 times y1 is y1 square, y1 square, plus y2 times y2 is y2 square. So the result in this case will be scalar. It is not vector anymore. It is just a scalar. So if you have vector, column vector, take the transpose, multiply it with the normal vector, then you will get a scalar representing this error, because this error is a scalar, as you can see. So this is the reason that we have here transpose. Okay, so now if you have y, we know what is y. Okay, here we have ax, because now we said that y is ax in this case. So ax minus y hat here is the actual y in the table, and ax is the equation. So when you take the transpose for this, the transpose will be distributed inside. So this will be a transpose, x transpose, but of course when you take the transpose, x comes here. Okay, and this will be minus y transpose, and then this will be multiplied by ax x minus y hat. Now you have this one over n, but you have here x transpose. From where this x transpose? This x comes here as transpose, a transpose times a, this is a, times x, this is x. So it is actually nothing but just simple linear algebra manipulations for those who have good background in mathematics. If you feel this as like puzzle for you, don't worry, you will not see such details in the quiz, but at least you know from where those came. Yeah, actually, this is the reason that actually I always prefer that you watch the recorded lecture before you come to the online session. Because if you watch the online session or the recorded lecture, you will not ask why this came, because it was explained in details on the board in the recorded lecture. Okay, and then we try to extend the analysis by using stochastic approach, because this approach is linear algebra approach but deterministic. And now in the stochastic approach, that we assume that the result y is the same as before as ax, but we add some uncertainty. This uncertainty can be noise, can be due to the biasing of the data. So we have problems in the data itself. So we represent all this by W. And then we try to solve it again, the same problem, solving it, but we keep in mind that we are now taking into account the uncertainty in the data. And it is very interesting to see that the final result, if under certain condition, that your data is zero mean, the noise is zero mean, and also data is Gaussian, even non-Gaussian can work with this assumption, then we can have, or we can reach to almost the same result. Actually, this is the result we got. So the result, it says that the optimum x is the same as we have seen before. Okay, so this is the optimum x, but before we had R inverse, here we called R A inverse, and before it was multiplied, as we can see here, this is R inverse, and here it was multiplied by A transpose times Y, and it is actually the same, but we call it like R A Y. The only difference between the both results, that this one is taken into like averaging condition, that we have a lot of data and we take the average of the results. The previous one, we assume deterministic data that we have. Here we assume stochastic data, and I have different like data. I used accumulation by having the averaging. So on the average, the results will be almost identical as it was shown here. We can apply the same concept with this data. So now assume that some person, okay, you know their like attribute. For example, the salary input, income, you know how much they pay for the rent, and you know the gender, and you know the a degree that they have, maybe bachelor or master or whatever, and you know their age. Our purpose now, you are like, assume yourself like a marketing person. Okay, now you are working in marketing and you want to guess the expenses that every person pay per year, per month, how much they pay per month. Okay, beside their rent, not included the rent. Because if you know the expenses of that person, then maybe in the marketing you can select the most proper prices for that person. Just take it like that. Now you have this data I have. So I will build my A matrix. This is my A matrix now. Okay. So here I have 5,000, for example. 5,000. Here you have 1,000. Here you need to put, because it is this gender, male or female, you need to represent it by a number. So you can put number for M and number for F. You can put, for example, -1 for M and 1 for F, or you can, it is better to put number, not 0. Okay. And for the degree also, you need to put some numbers here. Okay. For the age, you can keep the same age, or you can put ranges as I showed before, and so on. So now you can see that I put it in this way. So this is the A matrix. And then I have Y. Y is the expenses. Now you have this data. You are, as a marketing person, you have this data into Excel file. You want to generalize this data with equation. And when you have this equation and you have a new customer, and in the new customer you don't have how much they pay for expenses, it is enough for you to put this information in order to estimate what are their expenses. Okay, so now I have this A and I have Y. Then I use, in this figure, I use uh, the MATLAB here. I use MATLAB. So I put A. You can see this is A. Here I have like 1, 2, 3, 4. I have 4 rows into 6 columns. Okay. Then I have also Y. I have 4 cases. So this is Y. Then what is the optimum Z? The optimum Z is the inverse of A times Y. That's it. The inverse of A. It is actually A transpose times A, and you take the inverse, and B inverse, pseudo inverse in MATLAB will do that for you. So you don't need to make A transpose times A. This will be automatically done. This will be automatically done by using this function. It is called B inverse function. Okay, this BINV. The same function is used also in Octave. The same function B inverse, and other languages as well. They use this. It is different than inverse. Inverse of A, and just the A must be square matrix in that case. But B inverse, it can take the pseudo inverse that it can be applied directly. So now this is the parameters. This is the optimum parameters that you have. Now, if I have a new customer, but I don't know how much their expenses, I just take the new customer values, multiply it by Z, then I will get the expectation of their expenses. The same here for Octave. They use also B inverse, and also the same for Julia. But here for Julia, I need to make the inverse, but I take A times transpose of A and take the A transpose here. I need to do it myself. But I believe that in Julia also there is already function. It takes the B inverse. So for every language, you can find this inverse and you can calculate the optimum parameters. The final thing that I want to mention before we end this session is how could we deal with our data? When we have data, we can divide our data into 3 categories. The training data, the data that we use to train our model. Then the validation data. Part of the data, I will use it not was shown during the training. Remember, if you use the same training data for validation, then you will overlay the performance. Have you got what I mean? If you use the training, because the training of the data, your regression will be optimum for what? For the training. If you want to use part of the training, or if you have used part of the training or all of the training data, during the validation, it will be highly validated. It will tell you that the algorithm is perfect, but actually it is not. It might not, because you use the same training for validation. So for the validation, we have to use different data. Data was not shown in the training set. So I take that validation and I use that to check the generalization of my algorithm. If for the validation, the performance was good, it means that most likely nowadays I have like good performance machine learning algorithm. If it was bad, then I have a problem. This problem could be due to the overfitting, which known as memorization, as I explained last lecture, or it can be underfitting, where the algorithm is not enough to capture the relation between the input and the output. The learning and the validation, both of them, they are done by the researcher. But once the researcher has tuned his algorithm and claim that his or her algorithm is now perfect or not perfect, even very good, then they can apply it for some general data, maybe applied by other people. And then we call it like the test set. The test set with the algorithm go from your computer to be applied in real world. Then you can check how is the performance of your algorithm. I remember that one of my PhD students, he built one regression algorithm for in medical science. It was about expectation of certain disease, and we received maybe about 400 data set for the training and validation. So he divided, for example, 300 data for the training, and he used 100 for the validation. And the validation gave at that time maybe 85% accuracy, which was very good. But when we send the same algorithm to be tested by other hospitals, not in Helsinki, but in Brazil and in other countries, they found that the average accuracy was 68 or 67%. It is still okay, but much less than the validation that we did in the based on the data that we have. So the test set is like validation, but not necessarily that to be done by the same person. It can be representing the real world, like application of your machine learning algorithm. And this is some rule of thumbs how to divide your data among to be like in training or in validation. Yeah. So in general, you can see here that how the training is done. So this is during the training, as you can see. So during the training, you can see the error. This is the average error during the training process. And you can see that you can reach to zero error. But zero error, not necessarily that it means that good learning. This is very important to remember. Okay, zero error not necessarily means it is good indication for learning. Actually, it is the reverse. Usually, zero error means bad training or bad learning. Zero error in the training usually means overfitting, because you learn the data available for the training like exactly, which means that you don't only learn the general relation between the input and the output, but also you have learned the noise, the biases, everything. And then we have memorization, or overfitting is called. Okay, then if we look here as the complexity of the learning algorithm, when I should stop? Actually, you should stop based on the validation data. For example, I use this complexity. Maybe this complexity means that you use polynomial with third order, for example. Okay, and now I stop here. I test over validation. Okay, and then I increase the complexity. Of course, the training error will decrease, and then I check with the validation. So I can see that the validation is going down. It means that I can go further. So I check here. Maybe here is that we have polynomial with 6 order, for example. Then I check with the validation. The validation is still going down, and I continue in this way. But after some time, I will see that the error in the validation start to increase. Even the error in the training is going to decrease more. But once I got increasing in the validation, it means I have to stop here. I have to stop. This is the best generalization algorithm that I can use. Is it necessary to be good algorithm? No. Sometimes this is the best you can get, but still the best you can get is bad. It can happen. So what we can do, maybe you can change the paradigm of the learning process. I mean, instead of using polynomials, because here I use polynomials with more and more and more like order. Maybe I decided because the optimum one is still, the error is still very high. I am not interested, or I see that the accuracy here with the real data is only, let's say, 60%. So I am not happy with that error. Then I can think about deep learning. I can think about a neural network. I should look, maybe there are some missing attribute, missing features there. I need to find it. So I can start to think. And this is actually the purpose of this course. The purpose of this course is to make you thinking how to improve the situation. It's not only have data, but the learning, deep learning, get result, and if the result is bad, you don't know how to do. So now we can see how we can extend our thinking about the machine learning and how we can improve it further. Okay. Okay, so yes, here the question why it is better to put number, not zero. Sometimes when you put zero, you can remove the parameters from having any effect. Okay, because here you can say that, for example, you have y equal to, for example, a1 times x1 plus a2 times x2 plus a3 times x3, and so on. Okay, this is for linear regression. Okay, now if we have, for example, male and female, if I put male as 0 and female as 1, then for female, I will, for example, this is for the indication. A2 is the result based on X2. Is it male or female? So when A2 is 1, it means that it is male, it is female. And when it is male, I put it 0. When you put it 0, actually, you don't see the impact of this X2 on the equation. You just remove it. It doesn't mean that it is wrong, but it is better if you have 1 and minus 1. Then you can also judge where is the trend, or what is the trend. Is male or female expenses are more based on the salary, based on the education level, and also is this parameter male or female, does it have impact to increase the expenses or decrease the expenses? This information is important for the marketing, to see what subject that they can market, for example. So it is better to use numbers instead of this. This is the reason, but it is not wrong. Okay. Okay, that's all for today. Thank you very much for your participation. And the quiz is already now open. Don't open the quiz until you check the recorded lecture, and also to try to revise the previous lecture as well. So the previous lecture, when we talk about linear algebra, optimization, how to solve optimization problems, so it is important to check that as well. I will upload this lecture because it is recorded now. I will put it in the model. The previous lecture, it was also recorded and it was already uploaded. Lecture 2, it was uploaded already to the model, so you can find there that about the online session, and about this one also I put it in the online session as well. Okay, thank you very much and have a nice day, or rest of the day. Okay, bye.
Thank you, sir.
Thank you, Professor.
Thank you. Sorry that my voice, I have a little bit cold, so this is the reason that it was difficult to talk. But I hope that it was okay. Thank you.